Okay, two very quick topics, not really related to each other, except that they both have to do with springs. The first has to do with finding the equivalent spring constant when you arrange springs side by side. We could call that parallel. And when you arrange springs one after another, perhaps you would call that series. And in this case, with the springs parallel, the amount of stretch that you get would be the same for each spring. And so if you were to replace this by one spring, the equivalent stretch or deformation would be the same as the deformation in each one. The equivalent force exerted by that one spring would be the sum of the forces from each of the springs. And if we then go to Hooke's law, that the equivalent force is equal to the equivalent spring constant times the equivalent stretch, and so on for each of the other forces, but we've already asserted that all of these values are the same, so you divide those out and we get the result that the equivalent spring constant for these springs in parallel is the same as the sum of the spring constants in each of the individual springs, which you might recall from electric circuits is the opposite of what happened with resistors. Resistors in parallel, you did this goofy adding reciprocals. Resistors in series, you added the individual resistance to get the equivalent. It turns out, but I don't think we've talked about it yet, that when we get to capacitors, this is exactly the way that capacitors in parallel behave, which is very interesting because capacitors have a sort of a springy quality as they behave in a circuit. But at any rate, you are to memorize this. Springs in parallel, you add their spring constants to get the equivalent spring constants if this were represented by a single spring. When you put them in series, what's going to be true is that the force is going to be the same throughout. That's a kind of a tension issue. So the force exerted by these represented by one spring, the equivalent force, is the same as the force in each of the individual springs. However, the stretch that you get is going to be the stretch of this spring plus the stretch of that spring plus the stretch of that spring. So the equivalent stretch. And then again we go to Hooke's law and we replace the equivalent stretch by the equivalent force divided by the equivalent spring constant, and so on for the others. And then we divide out the forces, which are all the same, and this time we have that the reciprocal of the equivalent spring constant is equal to the sum of the reciprocals of the individual spring constants. Again, this is exactly how resistors behaved when they were in parallel, but now for springs it's the way they behave in series. And it will turn out when we study capacitors that it is the way that capacitors behave when they are in series. Memorize it. Apply it when you do homework. New topic. If you have a system with a spring, then the energy is going to either be elastic potential, which is equal to this quantity, 1/2 K, the stretch squared. But then, because we are looking at a simple harmonic oscillator, when you have a spring and a mass tied together, I'm going to replace the x here by it's the solution for that for a simple harmonic oscillator. And so I have the 1/2 K, but then for x I'm going to put in x max cos omega t plus phi and square that, which I can simplify a little bit and have the x max squared and then the cosquared of this argument. Hold on to your seats. The kinetic energy for a system of spring or elastic and mass is going to be 1/2 mv squared. But again, because this is a simple harmonic oscillator, I'm going to replace v by negative x max omega sine omega t plus v. That is, you take the derivative of this to get what the velocity is for the simple harmonic oscillator, and this was the solution to that equation, which again I distribute the square over these two. But then what I want to do is to add these two together. But before I add them together, I'm going to recognize that this omega squared for a simple harmonic oscillator is equal to k over m. That is, omega, the natural frequency of a simple harmonic oscillator, is equal to the square root of k over m. But then in this equation, the m's are going to go away, and you end up with a 1/2 k x max squared, just like here, except instead of cos squared, you have sine squared of the argument. So if you add these two together to get the total mechanical energy, the sum of the potential and the kinetic, you of course have this 1/2 x max squared, but then you have cos squared plus sine squared, which is a trig identity. That's equal to 1. So the total energy is conserved, and it's equal to that value when all of it is elastic potential. Or you could also say it's equal to that value when all of it is kinetic energy. That basically the point is that the energy stays constant, but it oscillates between being in the kinetic form and being in the elastic form. That the sum of those two stays a constant value, which is the maximum elastic energy, or if you like, the maximum kinetic energy. That as the elastic energy goes down, the kinetic energy goes up, and by exactly the same amount, so that the sum stays constant. Remind you of a picture that we had way back, but this was the picture for a pendulum, and we were looking at the energy sometimes being all gravitational potential when it's at an extreme, or partly gravitational potential and partly kinetic, or all kinetic when it's at the bottom. And that the energy oscillating back and forth between being all kinetic and being all potential, the total energy being constant for the system. Well, the same picture could be made for a mass on a spring, with the energy oscillating between not gravitational potential but elastic potential and kinetic, and the same kind of energy oscillating back and forth. I don't know if that's pretty, I don't know if that's valuable. It's a topic that came up in the book, so we talk about it. And that's all we're going to talk about. We done. Close the box.